Has anyone ever told you that they're such a bad cook that they can't even boil water?
But that's okay, because boiling water is actually way more complicated than you might think.
Well, to be fair, the boiling part itself is actually pretty easy, but it's what's going on inside this pot on a physical level that gets a little bit more complicated.
Boiling water is one of the simplest, most ancient forms of cooking, but the better you know the ins and outs of boiling, it's not just gonna make you a better water boiler, it's gonna make you a better cook.
I'm Kenji Lopez-Alt.
And I'm Katie Quinn.
And on this episode of the Food Lab, Boiling Water. Let's start by defining our terms. What exactly is boiling?
Boiling is when water gets hot, makes bubbles, and turns into steam. But there's a much stricter definition of the term.
And that is?
It's the phase transition from a liquid to a gas, which happens when the vapor pressure of a body of liquid is greater than or equal to the atmospheric pressure.
The cool part is that the energy in a given quantity of water is directly proportional to its temperature, and the atmospheric pressure is proportional to altitude. The higher you go, the lower the atmospheric pressure, and the less energy you need to reach a boil.
Exactly. At sea level, water boils at 212 degrees Fahrenheit. That's 100 degrees Celsius. But once you get up to, say, Denver, that's down to 203 degrees Fahrenheit.
And if you were to climb all the way to the top of Mount Everest, water boils at 160 degrees. That's barely hot enough to cook an egg.
What's really interesting is if you start working the other way, increasing pressure.
Now that is exactly what a pressure cooker is designed to do.
A pressure cooker is basically just a pot with a really tight lid. Throw food in it, put it on the flame, and then as moisture in that food converts to steam, the pressure in the pot builds.
Right, and as that pressure goes up, the boiling temperature also goes up. So most pressure cookers cook at around 250 degrees Fahrenheit inside, which is a good 38 degrees hotter than regular boiling water in a pot. At those temperatures, things happen really fast.
For a real-life illustration of this, we're gonna take two identical batches of pork stew, one in a pressure cooker and one in a covered pot, on the burner for 45 minutes.
The first thing we see is that the one in the pot is way paler than the one in the pressure cooker, and that's because a pressure cooker gets a lot hotter, and so more of those Maillard browning reactions occur, and that's also gonna mean more flavor in the end. So now let's take a look at the meat. So, they look pretty similar, but I think we're gonna find that if we try and shred this one, it's still pretty tough and rubbery. I'd say this is gonna take at least another hour, maybe 2 hours before this fully tenderizes. Meanwhile, the one from the pressure cooker, it's basically just falling apart, shredding.
Beautiful.
This kind of simple stew is what a pressure cooker is made to do. It's so much good flavor and so little effort.
Here's a question. Why add salt to pasta water?
So you might have heard that it's because it raises the boiling temperature of the water, and that allows the pasta to cook hotter. Or you might have heard that it makes the water boil more vigorously, and on the surface that seems to make sense because you've probably seen this happen. When you add salt to boiling water, it boils very vigorously for a few moments.
But in reality, salt has very little effect on the boiling temperature of water. A degree or two at most, not enough to make a difference in how the pasta cooks.
So what causes those bubbles? It's actually a thing called nucleation sites. See, when you add salt to a pot of boiling water, each grain of salt becomes the center of its very own tiny universe.
Yeah, we already know that boiling is dependent on temperature, but it also requires nucleation sites. Let's say that this straight line is the bottom of a pot. In a perfect universe, this would be perfectly smooth and perfectly evenly heated. As far as a bubble is concerned, that means there's no reason for it to form in one place over another.
And instead of forming, it'll actually just not form at all. The bottom of a pan really has these teeny tiny microscopic pits and valleys, and those things cause turbulence, and that's where the bubbles start to form. These are called nucleation sites, and they're responsible for everything from seeding the atmosphere to make artificial clouds, to the tiny ripples of turbulence in the early universe that caused solar systems and galaxies to form.
If you've ever been to a fancy function, you've seen this effect in action. Take a look at the champagne glass. Notice how the bubbles are rising from a few distinct spots, not just from the center.
And each one of those spots is a nucleation site. It's a tiny imperfection on the edge of the glass. You know, of course, we can also add our own nucleation sites by, say, adding a pinch of sugar to the champagne. You see that? So each grain of sugar is basically like a one-way ticket for the gases to escape into the atmosphere.
And that's exactly what happens when you add salt to boiling water. You're not so much affecting the temperature as you are adding a bunch of nucleation sites.
Right, but there's another good reason to add salt to your pasta water anyway, and that's because it makes your pasta taste better. If you want to see a really extreme example of nucleation sites in action, try dropping some mint Mentos into a bottle of Diet Coke. Just make sure that you stand way back.
Ask any old school Italian how to cook pasta, and they'll all tell you the exact same thing. In a lot of water, at least a gallon per pound.
The idea is that when you add room temperature pasta to the boiling water, it's going to cause the temperature to drop. And the bigger the volume of water, the less the temperature drop, and therefore the faster it's going to return to a boil.
So that seems logical enough. We've got 2 pots here to test this. One pot full of a lot of water, another pot not as much water.
If the theory is correct, when we dump this pasta in the water, the big pot should return to a boil faster than the small pot. You take the small pot, I'll take the big pot, we'll go at the same time, and let's see who wins. And as you can see, the small pot actually comes to a rolling boil faster than the big pot. And that's because even though there's a greater drop in temperature in the small pot, it also takes less energy to heat that small volume of water up again. That smaller amount of energy exactly compensates for the greater temperature drop.
And what's more, because of the greater surface area in the larger pot, it loses heat energy to the atmosphere faster, meaning that the smaller pot can boil harder and faster.
The really cool thing is that you don't even have to start pasta in hot water. You can take pasta, put it in a pot, cover it with cold water by an inch or 2, throw it on the stovetop, cook it, and by the time it's done, it will be completely indistinguishable from pasta that you started in boiling water. You know, I feel like we should end this episode with some kind of joke about how it's not the size of the pot that matters, but it's more like the ocean.
But instead, how about we just end with awkward silence?